Another well-studied permutation statistic is the major index. It was defined by a mathematician named Percy McMahon, who at one time was a major in the Army, which is how it got the name major index. Now, given a permutation in the symmetric group, let's define capital D of W to be the descent set of W. So that means that number of descents in W is the cardinality of this set. So precisely this is the set of indices I such that Wi is greater than Wi plus 1. Then we define Maj of W, which is major index of W, to be the sum of all indices in the descent set. So for example, if we look at S3, the permutations are 321, 312, 231, 213, 132, 123. The descent set of each is, let's see, we've got descents in position 1 and 2 here. 1 only. Position 2 only. 1 only. 2 only. And then no descents in 1, 2, 3. So the major index is the sum of these indices which are descents. So we have 3, 1, 2, 1, 2, and 0. And just for comparison's sake, let's put inversions here. So we have 3 inversions in 3, 2, 1, because 3, 2, 3, 1, and 2, 1 are 3 inverted pairs. Here we have 2 inversions, 3, 1, and 3, 2. 2 inversions, 2, 1, and 3, 1. 1 inversion, just 2, 1. 1 inversion, just 3, 2. And then no inversions. The distribution in both cases is 1, 2, 2, 1. Because we have 1 permutation with major index 0, 2 with major index 1, 2 with major index 2, and 1 with major index 3. Same as for inversions. In fact, inversions and major index are equally distributed on Sn for any n. Now recall that we let En be the set of substair words. Of length n. So that's the set of all words A1 through AN such that AI is between 0 and n minus I. So the first letter is at most n minus 1, the next letter is at most n minus 2, next letter is at most n minus 3. So these are words that would fit under a stair histogram if we drew the histogram of each word. And recall that if we define a map from the symmetric group to the substair words by sending a permutation to its code, that's a bijection. With the sum of the letters in the code being equal to the number of inversions in the permutation. The idea, if we want to prove the equidistribution of inv and maj, is going to be to define, let me just label this idea of the distribution, of the equidistribution proof. So we'll define another bijection phi from the symmetric group to the substare words by sending W to another word which we'll call maj table. And make sure this is a bijection. And make sure it satisfies some of the letters in the major index table of W equals major index of W. Then the composition psi inverse phi is going to be a bijection from Sn to itself. And this bijection satisfies major index of W equals number of inversions in psi inverse phi of W. So let's define this major index table and then show that we have a bijection, and that the bijection has the right properties, that the sum of the major index table letters are going to be the major index of W. So we'll define the major index table of W as follows. First of all, let's let W, so we're going to find several words that are W superscript some number. Let me define the n plus first one first. So we'll define W superscript n plus 1 to be the empty word, and we'll define the major index of this empty word to be 0, which makes sense because there's no descents in this empty word. Then we will look at letters starting with the greatest. So we'll start with N and go down to 1. And we'll define WI to be the subword of W consisting of letters I through N. And then this is really in the 4. So maybe I should call this A, B. Then we'll define m sub I to be the difference in major index between wi and wi plus 1. So the difference in the major index between what we have and the last partial word, which was only on letters I plus 1 through n. And finally, we'll define the major index table of W to be this word that we get by putting all the m's together, m1 through mn. So let's do an example. So let's let W be 1729 83564. And let me see if I have enough room here. I probably won't have enough room, but maybe I can use that after I'm done. So we'll look at the words restricted to 9, 8 and 9, 7, 8, 9, 6, 7, 8, 9, etc. So the word is nine, then 9, 8. If we look at 7, 8, and 9, then the word is 7, 9, 8. 6, 7, 8, 9 has the 6 afterwards, so 7, 9, 8, 6. 5 has it before the 6, so 7, 9, 8, 5, 6. 4 happens after the 6, so 7, 9, 8, 5, 6, 4. And then we'll look at the major index of each of these words. No descents, so the major index of Wi is 0. Here we've got 1 descent, major index is 1. 7, 9, 8, major index is 2. 7, 9, 8, 6, we have descents at position 2 and 3, so it'll be 5. 7, 9, 8, 5, 6, it's 5 again. 7, 9 is bigger than 8, 8 is bigger than 5, now 6 is bigger than 4. So we've got 2 plus 3 and another descent in position 1, 2, 3, 4, 5. So that's 5 plus 5 is 10. And then MI is the change in major index from what we had before. So 0, we went up by 1, went up by 1, went up by 3, went up by 0, went up by 5. Alright, now if we look at 3, 2, 1, the words are, alright, we'll have a 3 between the 8 and the 5. 7, 9, 8, 3, 5, 6, 4. And then when we insert the 2, that goes between the 7 and the 9. 7, 2, 9, 8, 3, 5, 6, 4. And then finally we get the whole permutation. 1, 7, 2, 9, 8, 3, 5, 6, 4. And the descents are 9 is bigger than 8, 8 is bigger than 3, 6 is bigger than 4. 7 is bigger than 2, 9 is bigger than 8, 8 is bigger than 3, 6 is bigger than 4. 7 is bigger than 2, 9 is bigger than 8, 8 is bigger than 3, 6 is bigger than 4. Let's see if we can figure out MI without actually computing the major index. So what happened here? When we introduced 3, these descents stayed the same, and that last descent got pushed over by 1. So that's going to add 1 to our major index. Then when we insert 2, that pushed these three descents one position to the right, so we've got an increase of 3, and then we introduced a new descent in position 1, so that's an increase of 4. And then when we introduced the 1, there's no new descent, but all the descents that were there, all 4 of them, got pushed one position to the right, so that's another increase of 4 in the major index. So that means the major index table of W is, we look at the insertion of 1, the insertion of 2 in that order. So 4, 4, 1, 5, 0, 3, 1, 1, 0. All right, and it's worth mentioning maybe that this bijection is due to Carlitz. Around 1950. So it's easy to see if there's 2 letters, then inserting a new letter is either not going to create a descent or it's going to create a new descent position 1. So the increase is 0 or 1. And for 3 letters, if we try the different possibilities, maybe we could convince ourselves that the major index is going to go up by 0, 1, or 2, depending on where we put that new least letter. But we need to show that if there's I ways to insert a new letter, maybe not I, if there's P ways to insert a new letter, then we want the major index to go up by 0, 1, 2, up to P minus 1. We want all P of those possibilities to actually occur with the different insertions of the new letter. Because if that's the case, then we know that the smallest letter in the major index table will be 0, the next one will be 0 or 1, the next one will be 0, 1, or 2, the next one will be 0, 1, 2, or 3, etc. And then we'll see that we have a bijection actually. The fact that the components add up to the major index, I guess, is pretty easy to see, because what we're recording is the change in major index every time we insert a letter. So if the major index goes up by this much each time, it makes sense that if we add all the increments by which the major index increased, then that sum would be equal to the major index. So the important thing to do here is to prove that we have a bijection. So let's suppose that we have, let's let U be this n minus I letter word, which is a permutation of the letters I plus 1 through n. So this is supposed to represent our subword Wi. Actually, Wi plus 1 is going to be the subword of our original permutation, restricted to letters I plus 1 through n. And now let's insert the letter I in all possible ways. And let's say that the permutation we obtain is v. So the number of possible insertions are, let's see, there's n minus I letters here. So n minus I plus 1 ways to insert the new letter, including before the first one and after the last one. So the n minus I plus 1 ways to insert I into U lead to increases of anywhere from 0 to n minus I in the major index. Alright, so that's what we're claiming. We've got a permutation of I plus 1 through n. We can insert a new smallest letter I in n minus I plus 1 ways. And if we do that, we want to see that the major index increases by all possible amounts between 0 and n minus I. So let's let k be the number of descents in our partial permutation ui plus 1. Well, sorry, just u. So this partitions the word u into k ascending subwords, which are sometimes called ascending runs of the permutation. So these are the subwords of consecutive letters between the descents. Let's call the initial position of each ascending run AK, which will be position 1 necessarily, AK minus 1, etc., down to, let's say, A naught. So we've got K plus 1 ascending runs. So the last one after the last descent is going to start at position A naught. And then the very first one before the first descent is going to start at position 1. So we have something like descent here, descent here, A naught is going to be the position after that final descent, and then there's K minus 1 segments here, K minus 1 indices from 0 to K inclusive. So this will be AK, AK minus 1, AK minus 2, etc. So those are names of the first position in each ascending run. then we'll label the other positions. Let's see how many other positions. N minus I minus k plus 1. So n minus I is the number of ways that we can insert a new letter, and k minus 1 is the number of places that we've already named. So we'll label the other n minus I minus k plus 1 positions from left to right. And we numbered these from right to left, but now we're going to label the other positions from left to right. We'll label them B1 all the way up to B n minus I minus k, n minus I minus k minus 1. And we'll label an additional position at the end. By b n minus I minus k. So that's if we insert our new lowest letter after the last letter. So now we'll look and see what happens to the major index when we insert the new letter in each of these positions. And when we insert a new letter, we push everything to the right, one position to the right. So now let's observe that the insertion of I into position AJ So if we insert the letter into position AJ of U, pushing everything else to the right. So pushing letters to the let's say U A J plus 1 up to U n minus I to the right. So the remaining letters. Now if we insert a new smallest letter into the beginning of any one of these ascending runs, we won't get any new descents because we've got a smaller letter following what must be bigger right here. But then smaller letter followed by the letter that used to be there is going to be an ascent. So we're not introducing any new descents. But if we insert the new letter into position AJ, then we're going to move J descent positions one place to the right, which increases the major index by J. So this increases J descent positions by 1 each. And therefore it increases the major index by J, which is anywhere between 0 and k. All right, now the sort of tricky part. What if we insert the new lowest letter somewhere in the middle of an ascending run? Then we're increasing a new descent and pushing several descents to the right, which increases each of them by 1. So suppose that we insert I into position